Hello, welcome to the last section in this unit, acceleration. Exciting. We've learned how to describe motion. We've talked about position, distance, and displacement. We've talked about speed and velocity, and we've even talked about momentum. Now we're going to look at something called acceleration. And acceleration is taking velocity and looking how velocity changes with time. When we talk about it, because in velocity, direction matters, so therefore, with acceleration, direction also matters. The things that we've been talking about where direction matters are displacement, velocity, momentum, and now acceleration. So if we take a look at the idea of speeding up, where our velocity is not constant, but it is changing and it is speeding up. We can look at that as our velocity going in this direction, acceleration going in this direction. We could also have our car slowing down. That is also called acceleration. A lot of times in our English language, we might say we are decelerating, but that's not what we say in science. We say we are accelerating negatively. We have negative acceleration. We're accelerating in a negative, it's a negative number, a negative value of acceleration. That would be slowing down. What happens if our car changes direction? We are also experiencing acceleration because we have our velocity, remember, is hinging upon the direction. So is acceleration. So let's take a look at acceleration. Acceleration is the change in velocity divided by the change in time. It's the rate of change in velocity. Remember, velocity is directional, so it does matter what direction I'm going. Another way to write this, lowercase a for acceleration equals final velocity minus initial velocity, because it's a change in that over the time it took to make that change. Velocity is always measured in meters per second, just like speed. It also includes the direction. Time is always measured in seconds, and acceleration, therefore, is going to be measured in meters per second per second. Whenever we have meters per second, that is the same as meters per second squared. Let's take a look at our velocity time graph. So when we have velocity on this side in meters per second, and we have time in seconds on the x-axis, what is happening right here? Well, right here, our velocity is 0, and it stays 0. So this object must be at rest. What happens now? What's going on right here? Well, right here, I have a velocity that is steadily increasing. So I have constant acceleration right here. My velocity is increasing. I'm not going to worry about talking about what direction I'm going right now. We'll just say I'm going in the same direction each time to keep it simple. But my velocity is increasing. And then what happens? No change in velocity. I'm going a constant 8 meters per second. So I'm not at rest, am I? Right here, I'm still traveling. I'm traveling at a constant velocity. I'm no longer accelerating. Now, what is happening here? We can look at this as a change in velocity. My velocity is changing. It's going to be a negative value. If I take my final velocity minus my initial velocity, I'm going to have a negative number. Therefore, I am negatively accelerating, right? Instead of decelerating, I'm a negative acceleration. And here, I'm stopped again. At time 10 seconds, I'm at 0 velocity once again. So here's an example. Let's say an ice skater travels at an initial velocity of 3 meters per second west, and then she stops and takes her all of 2 seconds to do that. What is the ice skater's acceleration? I'm going to write down my formula that I know about acceleration. Acceleration equals the final velocity minus the initial velocity over the time, the change in velocity over time. And I would like to understand what I know. What do I know here? I know that the initial velocity is 3 meters per second. Final velocity, I also know. She stops. So my initial velocity equals 3 meters per second. My final velocity would be 0 meters per second. How long did it take her? I know that too. The time it took was 2 seconds. This is a simple plug and chug problem. I can plug this value into here. I can plug this value into here. And I can plug this value into here. When I do that, my equation looks like this. And now I can go ahead and chug away on my calculator and find the answer. Here's my answer. I have a negative number for my answer. And I get that negative because 0 meters per second minus 3 meters per second is negative 3 meters per second. Negative 3 divided by 2 is negative 1.5, and my units are meters per second, or meters per second squared. So the ice skater's acceleration is negative 1.5 meters per second squared. That indicates that she's slowing down, which indeed she did. She stopped, didn't she? So let's take a look at some things we've discussed and some more things that we haven't about acceleration. Acceleration can be positive or negative, and since there are two components to acceleration, there is the magnitude of it, and then there's the direction. What direction is it? If you change either the magnitude or the direction, I mean, you can have it be positive or negative. If you're slowing down, it could be negative. Or if you're going, say, down or south, it might be negative as opposed to up or north. We can have constant acceleration, which means that you continually need to change your velocity at the same rate as time goes on in order to have constant acceleration. You can have changing acceleration, and that's easy. If you're slowing down, you're changing your acceleration. You're having negative acceleration by slowing down. Or if you want to take off really fast and get right up to speed, you come out of that stop sign and get right up to your 35 miles per hour really quickly. You had acceleration there for a period of time, and now you're going to go constant velocity where your acceleration is 0. So you can have changing acceleration. And I'd like to just take a look at these two terms, average acceleration versus instantaneous acceleration. And it's a similar idea to our average velocity versus an instantaneous velocity. Remember, our instantaneous velocity would be measured, our instantaneous speed would be measured by our speedometer, whereas the average velocity over a period of time, we'd have to figure that out. Similarly, we can do the same with acceleration. We can look at an average, our acceleration as an average over some period of time, or we could look at acceleration at one particular moment in time, and these would be very different. Or at least they could be different. They might end up being the same. So far we've been talking about motion in one dimension. Let's look at motion in 2 dimensions. And we're going to look at 2 different examples. One is projectile motion and the other is circular motion. Let's look at this idea of projectile motion first. First of all, everyone's tossed a ball to someone or watched balls being thrown in a sport or on TV. Earth's gravity causes the path of that projectile to follow a curved path. When you throw a ball, you'll notice it curves usually, unless you throw it straight up and it comes straight down. And even then, there is a point at which it reaches its maximum height and it comes back down. Unless it comes exactly straight down, it follows this very steep curve. Here's a less steep curve. Here is a curve. The important thing to remember, projectile, by the way, just means something flying through the air. In projectile motion, it's important to keep in mind that there are 2 components to the motion. there is the horizontal component and the vertical component. So when we look at velocity that is happening here with this particular projectile, the velocity that is happening, there is a vertical component to the velocity and a horizontal component to the velocity at each point here. Here's the vertical component and the horizontal component. And combine, those will give us the velocity of that projectile at that instant, the instantaneous velocity. But both components are needed to describe its velocity, to describe its motion at that time. So if we look at this, let's say this is the ball that this boy is throwing. Here's the path it's following, and here's the path. We're going to look at it, pick it apart a little bit. And as he throws this ball, there is both the, again, the horizontal and the vertical component. There is velocity contributed going up, and there's velocity that is contributed going this direction on the x-axis. Here is the very top of the trajectory. And as this ball starts to come down, what is happening is that we see the force of gravity is taking effect now and pulling this ball down. So there is a velocity that is negative at this point, going down. It is in the down direction, right? And as the ball continues, its horizontal velocity, if you kind of notice, the horizontal velocity remains constant. Here, if you look, the arrows represent the magnitude of some of these values. So here you see that the velocity is a lot greater. It gets smaller and smaller and smaller until it has no velocity at the very top of the trajectory. As it's coming down, its velocity is going to increase and increase. You can see that. Here's a little bit more, the downward velocity, right? The vertical velocity. More, 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 more. It's getting more and more vertical velocity. Its horizontal velocity is remaining constant as it's traveling. So as it's traveling this direction, this is remaining constant. However, we see a decrease in velocity and then an increase in velocity. So we definitely have acceleration going on in projectile motion. It's important to know that acceleration, this kind of acceleration, is due to gravity. And the acceleration due to gravity is always 9.8 meters per second squared. And we think of it as a negative number because it's always in the down direction. And acceleration due to gravity is always the same as long as we're on Earth. Now let's look at another motion that is two-dimensional, and that's circular motion. Let's suppose that we have a string here with a ball tied to the end of it. Here's our ball. It's attached with a string, and we swing that string around. Let's think about that motion and what is going on here. The velocity of this ball right here is in this direction. It's going some speed, this direction at some speed. And at this point now, it can be going the exact same speed, but this velocity has changed because it is now going in a different direction. At this point, its velocity has changed because it is now going a different direction. Even if its speed remains constant around here, its direction is changing. Therefore, it is accelerating. It's having a change in velocity over this time. The acceleration of this ball is inward, toward the point at which I'm holding that string. Acceleration toward the center of a curved or circular path is called centripetal acceleration. It's acceleration toward the center of a curved path. Here's some lovely examples of that. You've all probably experienced what that feels like, that acceleration toward the center of a curved path. You've certainly experienced it on a freeway. As you curve around this corner, your body wants to continue moving this way, and you're feeling as your velocity is changing direction as you're going around that corner, you're feeling that centripetal acceleration pulling toward the center, imaginary center of that circular path. Here are a few ideas. If you want advanced proficiency, how does the acceleration due to gravity compare on different planets? How would objects fall differently, and why? What would a speed time graph look like for changing acceleration? Or better yet, draw an example of acceleration versus time graph for different kinds of acceleration. How about when you interpret a speed time graph? What information can be obtained when you find the area under a curve or a line? Or any other great ideas you have. I look forward to seeing you in class and seeing what you have to come up with.